Hey, what's up, Mike?
Hello. Which is an umbrella group for about 9 different meetups in the Washington, D.C. area, all focused on different aspects of data science. And so we're really trying to build a community of practice here for folks in the D.C. area around data science related topics, of which statistics and text analysis are a significant part. We've got 4 co-organizers of Data Science DC. Jeff, who you all might be familiar with. Jeff, I don't know if you want to wave if he's on screen here. He tends to MC most of our presentations these days. Myself, Tommy, and then Chris Smith, who's also joined us. He's a new co-organizer of Data Science DC. Chris, I don't know if you want to say hi and wave.
Hello, everybody.
And she's not with us now, but Maria is also one of our co-organizers. So Jeff, Thomas, Chris, or M. Gander at datacommunitydc.org are how you can email us. And actually, I wanted to turn it over to Kelly, or if she's here, or David, to talk a little bit more about the text analysis interest group. All right, Kelly, if you want to take it away.
Hi, everybody. This is our second joint online meetup with multiple co-sponsors, as Tommy has already mentioned. As you know, in front of you, this is our fantastic new logo. And actually, I designed it, and we had a logo contest. So this looks like some kind of conversation. And then, you know, that will convey to bring the community together. So on this slide, there are several kind of, you know, incentives in terms of joining our TAIG. It's to bring together like-minded individuals like us right now in terms of text analysis and the related techniques, and increase the awareness, you know, in terms of community on, you know, our tools and methods. And finally, you know, really involve statisticians. And then also I want to really expand, because we said it's a big tent, right? So data scientists in research in this area. I just sent through the chat a couple of links about what we do, so I don't want to take time away from a fantastic presentation. So this is the second presentation that won last year's Joint Statistical Meetings, our TAIG sponsored contest. So hopefully this is really top notch, you know, presented by David. And last time everyone was really, you know, enthusiastic in terms of music mining. So that was also by Queenie, one of the attendees today. So as Dave said, you do not need to be an American Statistical Association member in order to be part of TAIG. And we really also want to collect at least 200 names in terms of petitioning as a section. For the time being, you can fully enjoy all the TAIG has to offer, and it's absolutely free. Not only for non-ASA members, but also for ASA members. So this is really an interest group that hopefully, you know, today's seminar will really give you further sort of flavor about the kind of things that we can do. And we really thank, you know, Data Science DC, Washington Statistical Society to really bring us all together with TAIG. Thanks.
Thank you, Kelly. So for Data Science DC and Data Community DC, we do have a code of conduct here. We want to create a respectful and harassment-free community for everyone. And so as a result, you know, I make it a point to try not to read slides to folks, but we're not going to tolerate any harassment or bullying in any way, shape, or form. So what I'd ask is, you know, if you see something, say something. And if we see something, we will say something. But feel free to reach out in a private chat over Zoom or send us an email. Again, I'm Thomas at datacommunitydc.org. Jeff is Jeff at datacommunitydc.org. Chris is Chris at datacommunitydc.org. If you see something that makes you uncomfortable, or you think there's an engagement that shouldn't happen, let us know, and we will take care of it as best as we can. We've also got a diversity statement. If we were here in person, like we had been in many years past, this would be the moment where I'd ask everyone to look around the room and see the ethnic and gender diversity of the entire audience, and tell you that our commitment to all of you is that we want our speakers to represent, to look like the community of the audience. And so we think it's really important to prioritize that. And so this is us making a commitment along those lines to ensure that we're showing diversity in tech leadership here. And I would ask the audience always hold us to that high standard. So Data Community DC has some sponsors. The Zoom membership is not free. Back when we were in person, and we will be in person again at some point when we are sure it's safe to do so. For those, pizza and empanadas were also not free. So we thank our sponsors for helping to fund our meetup and all others under Data Community DC. And I understand, Jeff, that we have an individual sponsor for Data Science DC. If he's in the audience when we get to community announcements, I wanted to give him a shot to say hi to everyone and talk about what they're about. But first, before we get to the broader community announcements, because we are selfish, I will start with the Data Community DC announcements. So Statistical Seminar has a couple meetups coming up, run by Mike Jadu, who I think I saw Mike's lovely face somewhere in the audience as I joined. Hey, Mike. So tomorrow there is best practices for contributing to statistical community forums. Is that right, Mike?
Yes, that's correct.
And then,
yeah, go ahead.
Oh, go ahead.
Yeah, we have 2 speakers for tomorrow, and they're going to be it's going to be a really good informative information session about how to contribute to statistical community forums like Stack Exchange and also our studio community.
Great. And it looks like you're having an introduction to strings in R and R Markdown on the 29th.
Yes, next Thursday. Yeah.
Great. And then I think the last one that I saw on the community calendar that was definitively scheduled, May 11th is our next Data Science DC meetup. We're going to be changing track radically away from the technical for a month and focusing on sort of career development. And so this will be a talk, Managing Your Manager, and we'll also be live recording it as part of a data science podcast. So really looking forward to that. And now community announcements. And I apologize, I don't have my notes in front of us, Jeff, but who is our sponsor and is he here?
Yeah, Gordon is here. You want to say a few words, Gordon?
Yes, thank you so much. I'm a professor from the University of Maryland, and we are proud to announce this new online exec ed program called AI Leadership for Healthcare. I put some link in the chat, you will see that. It is designed to upskill healthcare managers with AI vision, essential AI concepts, and implementation strategies. So feel free to check out more information, and you will be joining a cohort of leaders from MassDOT, Johns Hopkins, University of Maryland System, and IBM. Thank you.
Thank you, Gordon. So I wanted to give folks here who are in the audience a chance. If you have an announcement, if you could drop it in the chat really quick, I'll give us about 30 seconds. And Jeff, if I can rely on you, since when I'm sharing my screen, I can't see the chat. if anyone drops anything there to share it with the group.
Got it. Mike's got the info there for the Washington Statistical Society. If you want to.
It's WSS, fun times.
Always good stuff. Kelly's got some info here for a Breakthrough Fellowship Program, COVID-19. Check that out. There's a link on LinkedIn there.
Very nice. All right, and barring that, you know, I mean, the nice thing about being in a Zoom meeting like this now is if you have something, if you're scrambling for like a link for that job announcement or something, you can drop it in almost at any time just to expose other folks. So I will move on. And so now, David, I'm going to turn it over to you. I will stop sharing my screen. And I'll let you sort of introduce yourself and then get on with your research. I'm really looking, I was not able to attend your session at JSM this past year, so I'm really looking forward to hearing it.
Thank you. So can you guys see?
Yes, we can see your screen.
Okay, perfect.
I don't know if you want to go full screen so we can also see the
Yes,
preview.
that's
Yep,
fine.
there you go.
Exactly. Well, my laser pointer. Perfect. So
Very nice.
thank you, Tommy. Before I start, I just want to say today's talk is at least 60% different from what I presented last year because I continue developing this methodology. So just in case you some of you listened to my last year's talk, this one will be different. So about myself, my name is David, and I currently work in, I locate in Houston area, and I currently work in Houston Methodist Center for Outcome Research. My job title is a very general research statistician, but what I actually do is more like a combination of data scientist and the biostatistician. My background is in biostatistics, and now I'm pursuing a second master degree in biomedical informatics in UT Health. So in the past 3 years, I actually work in a different hospital. It's University of Texas Medical Branch, UTMB. It's another hospital in this area. I initiated this project there. So it's a collaboration with some faculties and a physician in UTMB. And also Dr. Roberts, he's a faculty in UT Health School of Biomedical Informatics. He's an expert in clinical NLP, and he's my mentor on this project. So in this project, I'll talk about NLP data pipeline, which is put a series of methods together for a real-world problem. And the problem is to extract information from scan documents from EHR. EHR is electronic health record. It's basically the hospital system that most hospitals use. So in this presentation, I'll talk about the motivation. I didn't start this project as a research, but instead it was to solve a data problem in one of the clinical research. It's a data problem. I'll talk about sleep apnea, scan documents in EHR, and I'll talk about sleep study, which is the kind of document we're dealing with, some related research. And the fun part is our data pipeline that involve image processing, optical character recognition, and NLP with deep learning. We designed some experiments, so I'll show the results and evaluation. I'll talk about conclusion and some future work take-home message. So it was back in 2018 and 19. I was working closely with UTMB's pulmonary clinic and sleep medicine clinic. They had a series of studies focusing on sleep apnea. Sleep apnea is the sleep disorder where patients would stop breathing when they sleep. And this would affect patients' sleeping quality and also long-term affects patients' health. The prevalence of obstructive sleep apnea, or OSA, in the United States is 3 to 5%. And the gold standard for diagnosis is through polysomnogram or sleep study. It's a lab test. This paper is something we published back in 2019. I put a reference here. It's using Medicare claims to look at COPD patients who also have OSA. And because sleep study is a laboratory test, and lab result is not available on the hospital claims. So in this data, we don't really have the gold standard. To proxy the population, we designed different algorithms. Like we look at any ICD-9 code for OSA, and you can see the number is way overshooting. We look at the CPT code, which is the procedure code on the billing for the sleep study, and the number is still too high because we only know these people had some procedure, some sleep study. We don't know the result. It's a mixture of positive and negative people. And we also look at positive airway pressure therapy, or CPAP. It's a mask, a DME device that helps to control this sleep disorder. So after the publication, a physician in the sleep medicine, she wants to look at the sleep apnea population in UTMB. So in that time, we were using EHR. And I thought, okay, now we're switching from claims data to a specific hospital's EHR. So supposedly we should have those sleep study results. So I just quickly wrote some SQL code to query the EHR system, and I got a whole bunch of missing null. So I looked into the patient charts, and this is what I found. Those are just reports with handwriting and scanned into the system. So basically, the workflow was laboratories generate this type of report. They print out, send, or fax to physicians. The physician read it without any documentation. They just read it, make their decision, and then they scan and upload to the EHR system. So yeah, these reports are in electronic format, but it is not a structured format because those are images in PDF files. There's no way we can use a program to automatically extract those information. So originally we thought that would be a quick project. It turned out we had to hire a group of people, research nurse, fellows, some unfortunate medical students to do this manual chart review. It took a group of people 6 months of time to go over 1,000 reports, manually write down the patient's information and the values we're interested in. I participated in the data cleaning, and trust me that there's no fun. It's just dirty and messy data, and it's expensive because we have to pay them hourly. It took a lot of time. And actually, we still have about 5,000 reports in the EHR system. We just don't have the manpower to go over. So after this project, I was thinking, is it possible we can train an AI to do this for us? That's why this project. Now let's sit back and look at what type of report we're actually dealing with. It's sleep study reports. So what a sleep study is, it's we let the patient sleep in the laboratory, like this figure. We put on monitor sensors and to continue reading the brainwave, eye movement, sleeping stage, vital, oxygen, and a lot of measurements overnight. In terms of types, there's diagnostic sleep study, which is done in laboratory. There's home sleep study, which is done at patient's home, doing similar things. And there's sleep night, which is the first part of the night we do diagnostic, and the second part of the night we put on CPAP, put on treatment, and continue monitor to see if the readings have improved. There are a lot of measurements in the sleep study report. Among them, we're most interested in apnea-hypopnea index, or AHI. And this is actually the gold standard for sleep apnea diagnosis. You can see if the AHI is low, that's normal. The higher, the worse. If it's over 30, that's severe. As a secondary outcome, we also look at oxygen saturation. So back in that time, it was 19, I think. Before I actually do anything, I look around to see if there were existing paper where I can reference. Unfortunately, it looks like scan document is not a hot topic, so not a lot of research has done that. I found an old paper back in 2012. It's comparing different optical character recognition engine for medical documents. So it doesn't do any NLP, just comparing different engines for processing the image and get the free text out of the image. This is a much later paper, a more recent paper published in UT Health, my current school. They were doing similar things as this study, but they were doing document classification. So they were doing high level, like in the EHR, there are some documents are billing, like invoice, some documents are clinical notes, some documents are patient consent. They are doing this high level classification. But there's very limited research focusing on information extraction, like pulling out specific value or some numbers from a scan report. So here's the overall, the big picture that I proposed. We start with image files in PDF format. We will do image reprocessing to improve the image quality, and then do optical character recognition, which is scan through the image and pull out the machine-readable text. And then with those texts, we can put it into a deep learning language model, and the model will output a structured label, structured values. And those values we can use in analytical files for specific research, like the one we had, or we can put in a database like EHR system for future usage. Now, a little bit detail about the development. The first step is we can query the EHR system and get those reports in image. And then, like I said before, a group of people already did those chart review on about 1,000 reports. So we can use that, secondarily use that as our label for training model and for evaluation. And then with those image reports, we do image reprocessing, do OCR to locate and recognize the text in image. And then we translate image into a machine-readable text. So basically, we're converting something like this into this. And with this free text, we can do NLP procedures like text segmentation, tokenization, and word embedding. Then we will translate this free text into a numeric form, like a high-dimensional array. And then use this array, we can train a deep learning language model. And after training, we can use the model to predict future reports or to deal with the 5,000 reports in the EHR that nobody has time to review. So that's the big picture. Our data source is UTMB's EHR, its EPIC system. We collected patients with at least 2 outpatient visits from 15 to 18, at least 18 years old, had some sleep disorder diagnosis. And among them, this is a big population. Among them, we random sampled 1,200 patients and had those people to review. And among those people, we pull out 990 sleep study reports. Now, I want to say this part is for the previous research. So in my project, we secondarily use this data. So you'll see some of the criterion is not necessary for my need, but it doesn't hurt. It's just that way. In order to use their data, I cleaned up some of their human annotation because for their purpose, they don't care about exact numbers. So they round decimal points. But for my purpose, I need exact matching. So I just recover those decimal points. And I end up with 955 reports that has complete AHI and SaO2 values, annotations. Now I can do image preprocessing. I referenced 2 papers and a blog. These two papers both use Tesseract. It's an open source OCR engine, and they both did image processing. So pretty much I looked at what they did. And this blog is a step-by-step tutorial showing how to use Python and OpenCV to process image. I want to say there's no single best way that will work for any kind of documents. A lot of time we just need to try and output and do these iterations until we get something look good. So I never say this is the best way or the only way. It's just something I did. I did grayscaling, remove all the colors because color usually is not relevant. I do delete and erode, meaning I make all the lines thinner and then recover it back with the same ratio. So during the process, some tiny noise will be removed. And then I apply some thresholding to increase the image contrast. You can see this part is before the pre-processing. There's a light gray background here, and after processing, this is gone. And before processing, this sentence used to be very light. And after that, we got a much darker text. So now we have better image quality, and we can do optical character recognition. I use Tesseract. It's an open source engine available online. Everyone can download it. I put reference here. So for their version 4, internally they use the LSTM. It's a recurrent neural network implementation. So basically what this engine does is we input an image like this, and the engine would output a list of words. You can see this, each row is a text, like this patient is from here, patient name is name, study date is from here. So basically it parts each word by word. And it also gives a location in pixels. This is the left top corner, and this is the width and height of the text. And it also gives a confidence, a probability that this region is this word. So in order to validate the engine's output, I use this location information to draw circles back to the original image. Then we can get something like this. We can circle each word that this engine can recognize. Then we can manually inspect it to make sure it's doing the job. Now, after the first thing after OCR is I identify the data because for patient information reason, I basically pull out the patient's information from EHR and match with whatever text we pulled and run some regular expression. And then whenever I found the patient name, MRN, or dates, it could be birthday, procedure day, whatever, it's protected by HIPAA. So I just put a placeholder to mask them. And all the data were encrypted. So at this point, we have converted text from an image into a machine-readable text like this. And now we want the machine, the pipeline, to read through these paragraphs and figure out this 16.3 is the AHI value we're interested in, because it says the apnea-hypopnea index AHI was 16.3. So at this point, this is the NLP problem. Our strategy is divide and conquer. So the first thing is sleep study reports can be very long. It can be anything from 2 pages to 28 pages. And there are a lot of paragraphs, a lot of sentences in there. So the first thing is we want to focus on those candidates. We know AHI and oxygen are both numeric values, so there must be some numbers. So we can write a regular expression, scan through the entire documents, and pull out all the numbers. Those are our candidates. We don't care about other words. For each number, we consider a window of 20 words around it. So that's a number in the middle, 10 words before, and 10 words after. This is something we call a segment. And most likely the definition of this number will be captured in this window. Like in this case, the apnea-hypopnea index AHI was 16.3. So we have enough information to tell this number is AHI. So we can convert each report into a list of segments. Like this 26 is here. there's 10 words before and 10 words after. This 19.5 is here, 10 words before, 10 words after. And using the human annotated labels, we know this value, 19.5, is AHI. This 26 is something else. So at this point, we have converted this problem into a classification problem because the segment is the feature, and we want to classify each value into a label, either something else or either AHI or oxygen or something else. But now the problem is still the segment here, although it is shorter, much shorter than the paragraph we saw before, but it is still free text. How do we handle that? The next step is further divided. It's called tokenization. So the idea is to cut text into a list of small units or tokens. Let's consider a segment like this. It's a string. We can split it by space. So we get word tokens. We get the apnea-hypopnea index AHI was. You can certainly argue that this is not actually a word. So actually there are a lot of ways to handle that. You can apply some filter, spelling correction. You can match it to a dictionary to force this into some predefined words. A lot of things can be done here. I'm just showing a quick example. Alternatively, we can do character level tokenization like this, just cutting it character by character. Good thing about character level tokenization is the possibility of each character is limited. It's just 1 byte, 256 possibilities, that's all. There are infinitely many possibilities for a word. But the best thing about character tokenization is each character doesn't have a meaning. A word has a meaning. Characters usually don't have a meaning. So in a later modeling step, if we use character, the model has to learn spelling. They have to learn the combination of this apnea is apnea. It has a meaning, and that's an extra step. Alternatively, there are other algorithms to do this tokenization, like this word piece embedding algorithm. I probably put the reference somewhere. Oh, here. I put parenthesis bird because the famous bird language model used this, and I will cover bird in a few slides. You can see basically it's doing word embedding, the index, but the way it handles out of dictionary word is like this. This word is something we've never seen before, so we split it into AP and EA. We split it into smaller pieces, and each of the pieces are already in the predefined dictionary. So I want to say tokenization is in general is a very flexible, very technical thing. It doesn't have to be humanly reasonable, like a word or character. It's just some way you can cut the words and make the following modeling easier. So once we have a list of tokens, the next step is word embedding. It's basically translating each token into a mathematical form, usually vectors. So you can think of very naive example. For each word, we can convert it into a one-hot vector, or we call this one-hot encoding. You can consider creating a vector with the dimension of all the possible words in dictionary, or all the possible words in the training data. For each word, we put a 1 in a specific dimension, like dog is 100, cat is 010, bird is 001000. It's very easy, but obviously there are some problems if we do this way. First of all, it doesn't consider clustering of natural language, because you can see each vector are equal distance to each other. But in reality, natural language, human language, because of the grammar, because of the meaning of words, there are clusters. Another issue is if we always convert the same word into a same vector, we're actually missing out information. Like this, apnea-hypopnea index AHI. The word index here, we are talking about this. But the same word in a different sentence, it could be a stock index, it could be a table index, or it could be a finger. Those are different, but not exactly different, I want to say. In my opinion, like apnea-hypopnea index and stock index are kind of similar because they are both aggregated number for some evaluation. And maybe table index and an index finger, maybe they're closer because they are both a pointer, a reference to something. Just my opinion, my understanding of English language. So I want to say it's kind of hard to draw a line and say this is a category and this is a different category. Sometimes the meaning of language is continuous. It's like a spectrum. So a more modern concept is called contextualized word embedding. The idea behind this is the meaning of a word is not only based on the word itself, but also based on where and how it is used in the language. So we can consider an embedding algorithm like this. We input a segment or a sentence, apnea, hypopnea, index, AHI, and we want the algorithm to assign a vector to each of the inputs, each of the words, each of the token. This assignment should be based on its neighbors, should be based on the entire segment. So if we input another sentence, a broken index finger, this index should have a different embedding, different vector, because of the different context. There are many algorithms to do this. Some famous one like word to vector, it's using SIBO or using skipgram to train. It's like one layer neural network. And there is Elmo, it's using bidirectional LSTM, a recurrent neural network, deep learning implementation. In this project, I used one of the most recent one. It's called BERT, and it's also probably the state-of-the-art method nowadays. BERT stands for bidirectional encoder representations from transformers. I put a reference here. It was published in 2018, and the software became available in 2019. It's a big and deep pre-trained language model. The original version, BERT Large, has 24 layers, 340 million parameters. And there's a smaller version called BERT Base with only 12 layers. In this project, for computation reason, I used the smaller one. And from this figure, you can see this is the first layer of BERT. It says here, layer 1, and there's times 11 layers here. So it means this part is repeated 11 times down here. So it's very deep. Basically, for a segment, it does the word piece tokenization, like I presented in previous slides, cut it into pieces, and then convert into a one-hot vector for input. Then this part is called self-attention layer. It's a very sophisticated algorithm to handle sequence. I also put a reference here. It's published in 2017 in the very famous paper called Attention is All You Need. So I'm not going to dig into details in this deep learning algorithm, but the point here is this algorithm would handle the position of inputs. So if you swap the order in the input sentence, the result will be different. The order is considered. And the second thing is it will consider all the relationships of different inputs, like I, fine, I am. Those relationship of tokens are modeled. And so after this self-attention layer, it will go through some linear layers and then pass down to the next layer. Next layer do the same thing. Repeat this 12 times. I think the interesting thing about this BERT model is the author not only proposed this architecture, they also pre-trained it. So the idea of pre-training is like, let's say logistic regression is the model. It doesn't come with a predefined parameter. It's just a model, and you use your own data to train it. But this kind of pre-trained model means the author also provides some initial training on the model. So when you download the model, it not only has the structure, but also has the parameter. And you can use it out of the box, or you can do a secondary training to make it more specific to your need. The model was pre-trained on food corpus 800 million words and Wikipedia over 2 billion words. So the actual training purpose, the training process was relatively simple. So the author input 2 sentences, sentence A and sentence B, concatenate together and put a separator, special token to separate them. And the training is very similar to how we learn English back in elementary school or high school. There are 2 types of quiz they ask the model to complete. The first thing is fill in the blank. So 15% of the input tokens were randomly masked. They are hidden from the model. And then the author asked the model to guess what those hidden tokens are. So the model will have to look at before and after to guess what those words are. And this will force the model to learn the spelling and grammar. The second task is guess the next sentence. So some of 50% of sentence B are actually the next sentence of sentence A, but another 50%, the other 50% were randomly shuffled. So the author asked the model to output a yes/no indicator whether sentence B is the next sentence of sentence A. And this will force the model to have a higher level understanding of both sentences in order to make this prediction. So after this training, if we cut down the output layer and use the last hidden layers output here, this will be actually a good representation of the language, because after training, the tokens, the inputs were transformed during these 24 or 12 layers, become a vector here. And this vector is used for the final prediction. And if the prediction is good, that means this hidden state is a good representation that considers the syntactic and semantic meaning of English language. So now the fun part is we can build our model. This is our model with all the details, but I'd rather use this part to explain it. So in our data, we have a structured data here, which is the location and the page number and the value, the numeric value. We also have a segment in free text. In our model, we have 2 branches to handle these 2 types of input. The segments go through the tokenization and embedding and dump into BERT, and goes through BERT, it will process the syntactic and semantic meaning and output a good representation here. For the structured data, we just go through 2 regular feed-forward neural network, and the information will stay here. So eventually, we use a classifier layer here to concatenate these two pieces. The idea is just whatever information we have, we put them together and use everything to make our prediction. The prediction is probability of each segment, each instance being AHI or oxygen or something else, a classification case. The actual training, we use 60% reports as training data, 10% for validation in order to do model selection, and 30% holdout test set for the final evaluation. We use cross entropy as loss function, and the training, or people usually call it fine tune, because bird model has been already been trained. We just tweak the parameters. The fine tune, I use a certain learning rate, sequence length of 32, batch size. This sequence length and batch size is highly related to your computer hardware, mainly the GPU's memory. I trained this for 200 approaches. So we can visualize the training process like this. The x-axis is approach. One approach means the model has been trained on the entire training data once. So you can see here, I trained for 200 times. And the y-axis is loss function. So we can see the blue line is training loss. It went all the way down. And the validation loss, the orange line, went down, and then somewhere here it started to increase. So this part is most likely overfitted. And then the actual programming I did was for each approach. After each approach, the model has been trained once, and then I make a copy, make a checkpoint of the model, save it in my computer. So that after training, I will got 200 versions of the models. And I look at this figure to say, here is the lowest point. Okay, this is the best model. Then I pull out that checkpoint as my final model. So with the final model, now we can use the test set for the final evaluation. Our evaluation includes segment level and document level. Segment level is just looking at the classification of each segment, each numeric value. So we can look at sensitivity, PPV, and C statistics, or area under ROC curve. And for the document level, this is something we really care about. So in the document, there are many numbers. All of the numbers are candidates. We choose the number with the highest probability of being AHI to represent the entire document. And the same thing for oxygen. We look at all the 100 numbers in a document and find the single number that has the highest probability and use it to represent oxygen. But instead of always choosing the highest probability, I don't want to force the model to make prediction when there's no enough confidence. So I set another criteria and say, if you look at the entire document, there's no single value has more than 50% chance of being AHI, then I don't want to predict. I would say missing, we don't know, no. So there's a labeling rate, algorithm labeling rate, means some of the reports are not labeled. Like in this case, the AHI, we can label 95.8% of the entire test set. In other words, there's 4.2% reports we cannot label. And I think that's also good because we know these reports we probably, in the real world case, we probably want to drop them, or we probably want to find a human physician to review them. Among those auto-labeled, we can look at how many are correct, that is precision. So in this case, we can achieve 98%. That means among these 95%, the algorithm labeled, 98% are correct. And this overall accuracy is among the entire test set, how many we can label and label it right. So that's 94%. I want to say, to achieve this performance, we actually use 70% of our entire data set. That is about 670 reports. In reality, when I say reality, I mean in the healthcare field, healthcare industry reality. I'm not saying the general industries. In reality, is we often don't have a lot of data. In NLP in general, human annotation is very expensive because you're taking people's labor and time to read and label. In clinical NLP, means NLP in the healthcare field or clinical field, it's even more expensive because you're not taking somebody's labor and time, you're taking professional people's labor and time. And even if we're saying unlabeled data, like just free text, a lot of time it is not available because of the EHR design issue, because of the clinical workflow, and because of HIPAA, health information protection. When I work on this project, I struggle a lot to actually get those data. Just getting those data already took me a long time. It takes, knowing somebody in the hospital, knowing the EHR system, getting approval, getting the administrative support. I can tell you a lot of story if you're interested, but that's not relevant to this project. So the real world problem is we don't have a lot of data, but we still want to build a usable model. Is it doable? So the next experiment, instead of using the entire training set, I subset 10 reports, 25 reports, 50 reports, and 100 reports. Those are independent subsets. Using each of the subsets to train the model, and then use the validation set to select model and evaluate them. So the idea is we use a very small amount of data to train a model to see if the model can still work. And this is the result in segment level. We see when the report, when the training size is small, every increase would the slope is higher, like the performance will increase more. And when it's from 50 to 100, the slope is much lower, which makes sense. And then this is document level, looking at document overall accuracy. With about 50 reports to 100 reports, the performance is very close to our final model. So in other words, with only 100 reports, probably we can already reach the best performance for the first model, for our model. So now this is just an idea of some application, a fun project, nothing to do with analysis or data science, just programming. So I input an image and then go through the processes using the output to draw labels on the image. So we can circle an area and ask the machine to put a label, say, this area is 19.5, is the AHI value, and the probability is this. So we can do like machine auto labeling, and we can embed this into a EHR system or some other programs to do some fancy things. Conclusion is we proposed a new data pipeline for extracting information from laboratory results. It is data-driven and requires less minimum amount of human labor, can be used for retrospective data collection or embedded with some existing EHR or database. And it has the potential to, I mean, although I only worked on Steve study reports, but it has the potential to use the same method for different kinds of scan documents. Limitations, our sample size is not big. So in the test set, the confidence interval is bigger. It doesn't work very well with messy handwriting like this one. Even I cannot understand what it is. So the OCR process would output some random characters or even consider this part as the image and totally ignore it. It doesn't work very well with tables because we input a horizontal sequence and we are missing out the header above. You know, table is a two-dimensional structure. We are not capturing that. Moving forward, I'm actually packaging this into a manuscript. I've done basically all the analysis and I'm writing it. So what I present today is only this part of the entire project. It's a smaller one. I actually did a lot of other modeling. I want to say this clinical bird here, I put the reference here. This is a newer model that is based on the original bird, but another group of authors did a secondary pre-training using clinical notes from EHR. So it's like if you say bird knows English from Wikipedia, then clinical bird is specific to clinical medical English. We did a lot of comparisons, and we see clinical birds can perform the best in segment level and document level. And we can see with smaller sample size, like only 25 reports, the green line is clinical bird. It already close to 90% accuracy, while bird is less than 80, and this LSTM is basically garbage. So that's about my project. The take-home message is, I want to say, my opinion, my observation, in the recent 2 years, I think NLP is having a big advancement because of the involvement of deep learning, hardware and software improvements. And another interesting thing is I noticed some open source community that we can do transfer learning more easily. So this is a website. I'm wondering if I can just share this with you. Can you guys still see my screen? I hope so.
Yep, we can.
Okay. Okay. So this is the website. It's a open source community where people can upload and download a lot of language models here. So like the bird-based model, I actually downloaded here. I just download and connect it with my deep learning network and use it. Super easy. And the cool thing is nowadays everyone can train your own language model. You don't need to design anything, just download the prototype using your own data to train, and then you can upload it back to the community. So for example, this is something I noticed yesterday. COVID, okay, hopefully this one, come on. So you can see this example, oh, this is version 2. They have a version 1. Okay, so this author, they collected, it says, okay, they use Bird large model as a starting point, pre-trained using the tweets about COVID-19. So they collected a lot of data. I can see here 22 million tweets. They trained it and then uploaded to the community. So if someone, like, if one day I want to do related research, this is my starting point. I don't need to go through the heavy amount of data for training. And I think this kind of community is a game changer because traditionally, like if you asked me 2 years ago, you asked me, does deep learning take a lot of data, a lot of computation power to train? I would definitely say yes. But nowadays, with this kind of transfer learning, meaning someone else pre-train the model for you, you only need to do the fine-tune part. And as we can see here, a deep learning model can train and can perform very well with very small amount, with only 25 reports. 25 reports, even logistic regression will not fit, but a deep learning can do that. And that is because of this community, this information sharing. So I think that's a very interesting and exciting news. So just sit tight, and I think the future is coming. Thank you.
All right, thanks, David. That was great. We had a bunch of questions come in while you were talking, so I figured I'd read them, and then we can jump straight into Q&A if that's all right.
Sure.
So the first one is, have you considered a QA system approach? I guess that's quality assurance system approach trained on Squad. Then you could have not labeled data queried against each document with a question like, what is SPI? And it could provide you the number. Let me reframe that question to say, what other approaches did you explore for doing this?
Yeah,
and
I
QA
like
was question answering.
Yeah, I know. I like that idea. And actually, I think one application is if we continue to develop this, of course, and we definitely, if we do that, we definitely need better software engineering and front end people, because you can see this is the best front end I can make. So yeah, I agree. We can do sort of like reinforcement learning, embedded this system into an EHR. And every time people, like a physician, upload this scan document, this model will run on the back end. And then there's a message show up and say, and ask the physician to confirm this is 19.5 is the AHI value our model find in this report. Is it correct? If it's correct, the physician clicking on yes, then this number will go to the backend database. If no, then physician can type in what it is, and we can use that information to improve our model. And I totally agree. There are a lot of interesting things can be done. But for myself, I'm a statistician, data scientist. I definitely need a lot of support, especially in the software level and in database level. So it's not something I can do alone.
Gotcha. And so another question here is, how is polysomnogram stored in an electronic health record? What metadata allows you to select these reports instead of, for example, ambulance transport reports?
You mean why I select that type of report instead of others?
I think it was sort of a question on how the data are stored in the electronic health records that let you choose particular types of reports.
I see. Yeah, I just figured I can read the chat here. Okay. Okay. So
it helps for the recording if I still say the question out loud.
No, I just figured out. So yeah, that's a good question. Actually, this is a great detail. So the polysomnogram is documented differently among different hospitals. And the way it's documented in UTMB is that on the clarity database, on the relational database, I can only see a hyperlink to the actual physical location. I don't have access to that. So I have to go through some administrative application, ask a health information management team to actually pull out that data for me. And that data polling is very preliminary. They have to do a lot of manual work, and the data collection was very slow and very difficult. So what metadata allows you to select these reports instead of other reports. I want to say, the reason I use this report is because I already have the labels. What metadata allows me to select is the hyperlink from Clarity database. So basically, I can query and tell the other team, say, hey, this report is something I want. Please get it from me.
Great. And how much computing power was required for your analysis? What hardware did you use, and how long did the analysis take?
Okay, yeah, I think if you Google this kind of topic, every year there are some people online and they will share benchmark saying these are the newest language model and image model in 2021 or 2020, and these are some GPUs, how long it takes to fit. In my case, I use NVIDIA's 2080 Super. It took how long? Several hours to train the model. I think 2 or 3 hours, I think. But it really depends on the batch size and the input sequence length. And yeah, that's pretty much it. And of course, how many training data you have. So there are a lot of factors. But I want to say there are benchmarks online. And if you really want to evaluate what kind of software and hardware you need, then there are resources available.
We had another question here about, I won't read it verbatim, but it's about typing versus handwriting for the optical character recognition. Did when you were using, I think it was Tesseract, was it able to pick out handwritten digits as well as typed digits? Did you notice a difference in accuracy and how well it performed, and did that affect your analysis?
Mm-hmm. Yeah, that's a good question, and that is I think one of my reference, like I said in an earlier paper, they focused on this type of evaluation. For my paper, I didn't seriously evaluate that, but just from my gut feeling is handwriting definitely are much worse. But fortunately, in my data, my source data, most of the reports are printed. The printing quality might not be very good, but important information are printed.
Gotcha. And another OCR question. How did you set the image contrast for the OCR step? And did you notice how sensitive it was? Did you consider optimizing for that variable?
Yeah, that is also something I didn't dig deep into. Yeah, again, previous paper did discuss that, and I just basically follow what other people are doing and also check the output to see, okay, this is probably good. That's why I didn't actually dig into that, to be honest. And I can share my algorithm. I think when I was writing my methodology, it should be somewhere. Anyways, if you want to, it should be. I mean, if you are interested, I can certainly. Like, okay, OC image preprocessing. So we did grayscaling, and then I did perform. Okay, I used the adaptive thresholding with threshold values. Okay, so that's a reference. That's all.
So I'm going to ask some of these questions out of order just because sticking with the OCR topic before turning off of it. Somebody was saying that their understanding is that Dropbox has a state-of-the-art OCR, even for handwriting. Did you look at Dropbox's OCR, or did you just look at
No,
the
I didn't know
Tesseract?
that. Thanks. I will check that. I didn't know that.
Yeah, I also didn't know that for the record. So going back to sort of the modeling, have you tested how generalizable your model is? Have you seen if it can accurately detect other conditions or values?
You mean other conditions in the same type of reports, or other type of reports? I think so. The thing is, our data, our human annotation only did AHI and oxygen, and it's only focused on this type of report. So right now, I'm also actively looking for different collaboration. Like if someone else has different type of skin documents, I'm very happy to try my algorithm, my pipeline, to see if it can be generalized. I don't know.
Gotcha. And what other types of neural network architectures did you try before settling on your current one?
Yeah, sure. Let me pull out here. So here this slide. Let me make it bigger. So I tried. Okay, the question is neural network. Okay, so I use LSTM, long short-term memory, which is a recurrent neural network. I tried two ways of word embedding. One is the naive one hard encoding, and I also tried word to vec using SIBO and pre-train on the entire training data. So and then I tried bird and clinical birds. So that's the four deep learning models I tried. And I also tried some word-back models using traditional machine learning algorithms.
It'd be interesting to see the comparison of how, if all of those models made it through to the end of your pipeline, like the accuracy differences, or even something that's not as quantitative. Oh, well, and there you go.
Yeah.
How easy was it to work with those various different models?
That's a very good question. So overall, I would say if you look at this document level accuracy, deep learning model in general, especially these models, these bird and clinical birds, LTM, they perform much better than word-back models, which is only 87, 89, less than 90% accuracy. But those models will require GPU to train, or if you run on CPU, that would take days. So in terms of implementation, I think traditional models would take, if you want good performance, it would take more time to manually create some features. Like in this case, I only use a very simple, I use TF-IDF. It's basically a weighted term frequency. They didn't dig into that, but I noticed in some earlier papers, especially before 2015 or 14, where deep learning became popular. In older times, people often use support vector machine with maybe 100 or 80 features. And that's a huge amount of programming for people. The good thing about using deep learning is people don't need to do a lot of work in programming. But on the other hand, the computer needs to do a lot of work.
I just have to reflect on what you just said about, I think, how far deep learning has come. As when I was first hearing about it in probably around 2013 or 2014, it was extremely hard to use, and you were programming gradient descent yourself in C and C++. And now, with the way the frameworks have evolved, you're not the first person to say that in many cases, deep learning can be easier to work with because they've done so much work on making the framework easy to program.
Yeah, thanks for pointing out the historical background. Yes, that is totally true.
My, how far we've come. So since your pipeline was so involved, what did you do to manage it?
So right now I'm sort of proposing it and developing it and also introducing this to people who might be interested in it. So we haven't actually put it to production yet. So there's no management at this point. Right now it's just myself in one or two computers working on things. I gave this talk last week to Houston Methodist to their center, and they also have high interest on this. They want to use this pipeline to solve their data problem. So hopefully moving forward, I will have some collaboration, and then I can actually put this to production.
Yeah, good luck. So the last question here. What is the best way to reach out to you for more detailed questions about your work?
Oh, I have an email. Let me type it here. Okay, can you guys see it? Oh, no. Sorry, I was sending, okay, everyone. Okay. Okay.
All right. And with that, David, thank you so much for taking the time to share your work with us. This was a great talk, and it's really interesting to see how you pulled together so many different parts into creating this big pipeline.
Thank you guys for your feedback.
And just a reminder for everyone, we will post the talk and the Q&A on the Data Community DC YouTube channel here within a few days.
Thanks.
Thanks, everyone.
Thank you.
Hello.